For as long as we've understood what the sun is, we've dreamed of bottling its power. I'm talking about fusion energy. Clean, safe, and for all practical purposes, limitless. For a long time, it's been the holy grail of energy science. Well, that dream? It's now closer than it has ever been before.
If you've been around science circles for a while, you've definitely heard the old joke. Fusion is the energy source of the future, and it always will be, right? For decades, progress felt like this slow, steady, but kind of endless marathon. The finish line just never seemed to get any closer.
But something has fundamentally changed. And let me tell you, that joke isn't funny anymore because, well, it's just not true. In the last few years, that marathon has turned into an all-out sprint. Breakthroughs aren't just happening here and there. They're accelerating at a pace that is honestly just breathtaking.
Just look at this timeline. It all kicks off in late 2022 when the National Ignition Facility, NIF for short, achieves what many thought was impossible, ignition. And from there, it's like a cascade. We see new records for endurance from one lab, then another lab shatters barriers in power and density, and then NIF comes back and just smashes its own record, quadrupling its energy gain. This isn't just one single event, it's a chain reaction of incredible progress.
So how are they doing it? Let's start with the classic approach. Think of these as the marathon runners of the fusion world who have suddenly, out of nowhere, found a new burst of speed.
So this is a tokamak. The basic idea is you have to create a plasma that's hotter than the core of the sun, and then you have to hold it in place so it doesn't just melt your entire reactor. So what's the solution? An invisible container, a cage made of incredibly powerful magnetic fields. I love this analogy. It's basically the universe's most advanced magnetic thermos, and it's designed to hold a tiny star.
And what's really cool is how different teams are tackling different pieces of the same giant puzzle. You've got the East Tokamak in China, which just broke a critical density barrier. That means you can pack more fuel into the plasma, which means more power. At the same time, over in Europe, the West Tokamak was focused on endurance, proving the machine itself can actually survive these absolutely hellish conditions for longer than ever before.
Over 22 minutes. Now that might not sound like a lot, but for a fusion plasma, my gosh, that is an eternity. This record isn't just about ticking a clock, it's proof that the materials, the engineering, the whole design, it can handle the immense heat and radiation, and that is an absolutely crucial step for building a real power plant.
So, the magnetic bottle is getting better and better. But an entirely different approach just had a breakthrough that completely changes the game. What if, instead of trying to contain a star, you could just create one for a split second?
And this brings us to probably the biggest fusion story in a generation, ignition. This isn't about sustaining something for a long time, it's about creating a single, unbelievably powerful flash of creation.
This is what's called inertial confinement fusion. So forget the magnetic thermos for a second. Think of this more like a laser-powered piston or a cosmic hammer. You take nearly 200 of the world's most powerful lasers, you fire them all at the exact same time at a tiny fuel pellet, and you crush it with so much force that for a billionth of a second, it becomes a star and releases this incredible burst of energy.
Okay, so back in December 2022, the National Ignition Facility, NIF, they made history. For the first time ever, they got more energy out of a fusion reaction than the lasers put into the fuel. But as you can see from this chart, that wasn't a fluke. They did it again and again, and then in April 2025, they completely shattered their own record. Over 4 times the energy. Just let that sink in for a moment. They fired about 2 megajoules of laser energy at the target and got over 8 megajoules of fusion energy back out. This is the moment, right here, where science fiction really started to feel like science fact. So how in the world did they make such a massive leap? Well, the secret wasn't just in making the lasers more powerful. It was in the tiny little target itself. More specifically, a perfectly engineered diamond.
The innovation here has this very technical name, continuous gradient doping. But the idea is brilliant. See, the problem was that the intense X-rays from the initial implosion could mess with the fuel before it fully compressed, making the whole thing less efficient. To block those X-rays, they add a tiny bit of tungsten to the diamond capsule. But just dumping it in there created other problems. So, what did they figure out? They figured out how to add the tungsten smoothly, gradually, kind of like a dimmer switch. And that one change made the implosion more stable, the fuel stayed cleaner, and the final fusion burn was way, way more powerful.
Now hold on, because this race isn't just between massive government labs anymore. A whole new force has entered the field, and they are moving with incredible speed and agility. I'm talking about private companies.
And they are hitting major milestones. You have Tokamak Energy, which just hit a record 1 million amps of current in their machine. That's a key measure of power. And at the same time, you have General Fusion proving their totally unique compression system could get a 190-fold increase in fuel density. These are not small steps. Let's talk about Tokamak Energy over in the UK. They're proving that smaller can be seriously powerful. Their compact spherical tokamak, it's a different shape, recently hit that plasma current of 1 million amps. That's a massive milestone. They're showing that a leaner, more agile approach can still break records, and it might just lead to a faster, cheaper way to build a power plant.
And then you've got General Fusion, which is doing something that's, well, it's a hybrid of everything we've talked about. They start with a stable plasma, kind of like a tokamak, but then they compress it mechanically with a spinning vortex of liquid metal. The analogy is perfect. They are literally squeezing a magnetic bottle to trigger fusion. It's wild.
And their recent tests have validated their core computer models. This quote here really says it all. The goal in the private sector is crystal clear. Find the most practical and cost-efficient path to get fusion energy onto the grid. They're not just doing science for science's sake, they're building a business.
So you've got all these different teams, all these different technologies, all racing forward at full speed. So what happens next? Are we really heading for a photo finish?
This pretty much sums up the state of the race today. You have three major contenders. You have the magnetic bottle approach of tokamaks, which are now setting new records for endurance and density. You have the laser piston of inertial fusion, which has now achieved that massive 4 times energy gain. And you have the liquid squeeze from the private sector, which has just proven its radical new tech actually works.
And I think this is the key takeaway. It's not about picking one single horse to win this race. What we're seeing is multiple, parallel paths all closing in on the same goal. The finish line for fusion energy is finally coming into view, and it's being approached from all sides at once.
All those decades of slow, patient, grinding work have laid the foundation for this incredible moment. The era of fusion is always 30 years away is definitively over. It is now a full-throttle sprint. And that leaves us with the most exciting question in all of science today. Not if we will finally harness the power of a star on Earth, but simply how we'll do it and when.